Wormholes, sometimes called Einstein-Rosen bridges, are fascinating objects predicted by the theory of general relativity. They have captivated the imagination of scientists and science fiction fans alike because they seem to offer the possibility of shortcuts through space and time, bypassing the vast distances that separate stars, galaxies, and even different points in time. A wormhole can be visualized as a tunnel connecting two different points in space-time, much like a bridge between two separate locations. Instead of traveling along the curved surface of space, like moving from one side of a mountain to the other, a wormhole would let you cut through it. This could, in theory, allow for incredibly fast travel between distant parts of the universe or even across different times. Wormholes stem from Einstein's theory of general relativity, which describes gravity as the warping of space and time by mass and energy. In 1935, Einstein and his colleague Nathan Rosen proposed the idea of a bridge or tunnel connecting two black holes. Mathematically, this structure seemed plausible, though there are major hurdles to its physical existence. There is no direct evidence that wormholes exist. However, the mathematics of general relativity allows for their theoretical existence. Scientists believe wormholes could form under certain extreme conditions where space-time is highly curved, such as in the vicinity of black holes or other dense objects. Still, several issues make them highly speculative. Stability. Most models suggest that wormholes would be inherently unstable. They could collapse too quickly for anything, even light, to pass through. A theoretical solution to this is exotic matter, a type of material with negative energy that could keep the wormhole open, though no such matter has been observed. Size. Even if wormholes could exist, they might be incredibly small. Some theories suggest they could be as tiny as subatomic particles, though it's also possible that in certain conditions, large wormholes could exist. Quantum mechanics versus general relativity. There's an ongoing tension between general relativity, which governs large-scale structures like stars and galaxies, and quantum mechanics, which explains the physics of very small particles. For wormholes to be physically possible, a theory that unites these two forces, known as quantum gravity, would likely be necessary. String theory and loop quantum gravity are two candidates for such a theory, but they remain incomplete. If a stable, traversable wormhole existed, you could potentially enter one end, often called the mouth, and almost instantly emerge on the other side, no matter how far apart these points are in space-time. For example, if one end of the wormhole was near Earth and the other end near a distant star, traveling through the wormhole would allow you to bypass the vast distances that would normally take thousands of years at light speed. This shortcut effect is sometimes compared to the idea of folding a sheet of paper. If 2 points are on opposite sides of the paper, a wormhole is like punching a hole through the paper, effectively bringing those points together. One of the most intriguing possibilities is that wormholes could be used for time travel. According to some models, if one mouth of a wormhole moved relative to the other at near light speeds, it could create a time difference between the two ends. Entering the wormhole on one side might allow you to emerge on the other side at a different point in time, either in the past or future. However, this leads to paradoxes, like the famous grandfather paradox. If you traveled back in time and prevented your grandfather from meeting your grandmother, how could you exist? These paradoxes raise significant challenges to the idea of using wormholes as time machines. Even if wormholes could exist, there are several significant challenges. Exotic matter. Keeping a wormhole stable would require negative energy or exotic matter to prevent its collapse. Though physicists have created small amounts of negative energy in laboratory conditions, like the Casimir effect, it's unclear whether it would be sufficient for stabilizing a wormhole. Black holes and wormholes. Some black holes may contain hidden wormholes within their event horizons, though anything entering a black hole is torn apart by tidal forces before it can access a wormhole, making travel through one highly impractical with current knowledge. Quantum entanglement. Recent advances in quantum mechanics suggest a connection between quantum entanglement and wormholes, particularly in the theory of ER equals EPR, proposed by physicist Juan Meldacena. This theory posits that quantum entanglement (EPR) and wormholes (ER) might be two sides of the same coin, though this remains highly speculative and mostly theoretical. Wormholes remain a fascinating and highly theoretical concept. While the equations of general relativity allow for the possibility of wormholes, several hurdles, like stability, exotic matter, and quantum gravity, must be overcome before we can say with any certainty that they could exist in reality. Even if they do, traversable wormholes may remain far beyond our technological reach for the foreseeable future. Nonetheless, wormholes continue to inspire scientists who are probing the nature of space, time, and the universe in search of new understanding. In short, while wormholes could theoretically exist, they remain a speculative possibility grounded more in mathematical models than physical reality for now. Thanks for watching.